Hey, so this is Kyle Hayden. I'm going to be talking today about ascending surfaces, complex curves, and not Floer homology. The question that we're going to start out with today is a question about complex curves in complex Euclidean 2 space, but it's going to touch on ideas from knot theory and contact geometry. So to begin, let sigma be a smooth complex curve in C2. And by that, all I mean is a smooth surface which is embedded in C2 with a complex structure on the surface such that the inclusion is holomorphic. But to be concrete, we could do something like choose a polynomial and two variables and look at its zero set. And in this case, we have this particular polynomial that has nothing to do with my birthday, and its zero set is going to be a smooth complex curve. The question we're going to want to focus on is, what does this complex curve look like? Okay, and in particular, I'm going to take a three-dimensional perspective on this and think about what it looks like from the perspective of knots in S3 if we intersect this curve with some round three sphere in C2. So our attempt to answer this question is going to take us through a couple interesting areas. So for one thing, it's going to shed light on knots in S3 and complex curves in C2. But it's also going to lead to a more general class of surfaces that are related to complex curves and symplectic and Lagrangian surfaces. And they're going to be of infinite interest, in particular because they shed light on the behavior of invariance of transverse and Legendre knots in knot Floer homology. And then finally, the techniques and the results we're going to talking about today generalize really naturally to the study of complex curves in Stein surfaces. So a Stein surface is a complex surface that emits a proper holomorphic embedding into some complex Euclidean space. Okay, and a special note about that, basically any time in the talk today you see the four manifold S3 times an interval, you can replace that with the Stein cobordism between contact three manifolds, and generally speaking, the results will hold true. Okay, so to tackle our question, we start out with some complex curve in C2, and we're going to intersect it with a pair of three spheres and think about the knots or links that we get and how they're related. So in particular, we want to assume that this complex curve is smoothly transverse to these particular three spheres. And now the question is, what's the relationship between the links that you get when you intersect the complex curve with those three spheres? So the first observation I might make is that if the complex curve is transverse to all of the intermediate three spheres between radius A and B, then there's never any change in the topology of the surface, and in particular, K prime is smoothly isotopic to K. So the real question becomes, what happens if there's a point of tangency between sigma and some intermediate sphere? And so the main theorem that we're studying today explains this, and we're going to frame the answer in terms of braids. So if sigma is a smooth complex curve that's transverse to the three spheres at radius A and B, and K is the intersection of sigma with those with the sphere at radius A, and K prime is this intersection with the sphere at radius B, then K and K prime have braid representatives beta and beta prime, and beta prime is obtained from beta by three operations. You can add a new strand, which corresponds to a local minimum. You can add a positive generator, which corresponds to a saddle. And you can perform braid isotopy and positive braid stabilization and destabilization. And so these three operations on braids have schematic pictures down below, and these will sort of provide the toolkit where we can imagine seeing a complex curve at various radii. These will be the moves that relate to level sets. Now, the one thing I want to clarify is that I'm not actually saying that the genuine links that you get by intersecting the curve with S3 are already braided and that you see these moves relating them, but rather each level set can be braided in such a way that passing critical points gives rise to the local behavior shown in the figure below. Okay, and so we'll interpret this as a sort of topological description of what's happening to the complex curve as we intersect it with spheres of different radii. So to illustrate this, we look at a particular complex curve, which is topologically a disk, and its intersection with some sufficiently small three sphere is going to be empty, and its intersection with some larger three sphere is going to be the knot 820. Okay, and so what we have here is a sequence of diagrams. And so starting on the bottom left with the empty set, we see a pair of minima that give rise to a two-component braided unlink. And then we see a positive stabilization. Okay, after that, we see some braid isotopy. And I encourage you as an exercise to pause and actually check that those two braids on the right are actually isotopic as braids. Okay. And then finally, we see in the top, going from right to left, the introduction of a positive crossing, and that's corresponding to a saddle. And so here we sort of see several slides that indicate the topology of the surface as you increase in radius. Okay. So a couple of remarks. First thing, the proof of the theorem one relies on characteristic foliations and open book foliations on surfaces. And what are these? Well, if you have either a contact structure on a three-manifold or an open book decomposition of a three-manifold, that lets you define a singular one-dimensional foliation of any surface sitting inside of that three-manifold. And so by using these techniques and extending them to the four-dimensional setting, we're able to convert some information from the complex geometry, the complex curve, into contact geometric information, and then finally into braid theoretic information. And then the theorem, as stated, generalizes really naturally from C2 to arbitrary Stein surfaces using braids and open books. And so the one difference is that in this case, you'll also have to allow for changes in the ambient topology of the four-manifold. Whereas here in C2, we have some natural Morse function, which only has a minimum at the origin, and then the topology of the ambient level sets, the three spheres, never change. Okay. So moving on to thinking about applications, we can quickly recover the following theorem of Boileau and Arevkov, which says that if I have a knot in S3 that bounds a smooth piece of a complex curve in the four ball, then that knot has to be isotopic to the closure of a quasi-positive braid. So quasi-positive braids are a natural class of knots and links introduced by Lee Rudolph. And to define them precisely, we want to recall that a braid is said to be positive if it's a product of the positive standard generators of the braid group. The braid is quasi-positive if it's a product of conjugates of the positive generators. And so you're allowed to conjugate by arbitrary words. But the key is that this is a natural generalization of positive braids. Okay. And the original proof of this result due to Boileau and Arevkov uses the theory of pseudo-homomorphic curves due to Gromov, and in particular the positivity of intersections between pseudo-homomorphic curves due to Mikolev and White. Whereas the proof that we give uses more elementary three-dimensional techniques. Okay. So both to hint at the ideas of the proof, but also to hone in on the applications, we need to introduce some contact geometry into the picture. So I want you to recall the standard contact structure in R3, and it has this nice rotationally symmetric depiction. And we can extend this over a point at infinity to get the standard contact structure on the three-sphere. And while that's a useful description for visualization, there's a more geometric description of this contact structure on the three-sphere that's useful for us. And it's that the contact structure in the three-sphere is exactly the set of complex tangent lines to a round sphere in C2, such as the unit sphere. So more precisely, the contact plane at a point in the unit three-sphere is the unique complex line in the tangent space to the point inside the three-sphere. So that'll be a real three-dimensional vector space inside of the tangent space to the point in C2, which will be a real four-dimensional vector space. But the point is that that three-dimensional subspace has at most one complex line in it. And indeed, it has exactly one complex line in it. And that would be the complex plane, or the contact plane. Okay. So now, with this extra information in hand, we want to return to our initial question and say, well, now, not just from the perspective of these three spheres topologically, but from the perspective with the contact geometry, what does a complex curve look like? And so this is what motivates the more general class of surfaces that we're going to study. Okay, and so these are called ascending surfaces. And so this definition is originally due to Boileau and Arevkov for surfaces in C2. And so the definition is that a smooth oriented surface in C2 is an ascending surface if the radial distance function restricts to a Morse function on sigma, and the regular level sets of this Morse function have to be oriented links that are transverse to the contact planes of sigma on each level contact 3 sphere. And then finally, at the critical points of F, the surface must be tangent not only to the 3 sphere, but it must be tangent to the contact plane inside the level 3 sphere. Okay? And so moreover, we can say that it's a positive ascending surface if at those critical points, the orientation on the surface coincides with the natural orientation on the contact plane as a complex line. So the thing which ties this definition into our broader question is the following lemma, which is that indeed any complex curve is a positive ascending surface, with the one caveat that we might need to do a slight perturbation first. So the only reason we need to do a perturbation is to ensure that the restriction of the radial distance function is Morse. But this can always be achieved by an affine complex translation. Okay, so because this sort of fits into the details, I'm not going to go through the proof, but I will put it up on the screen in case you want to pause and read through it for the moment. Okay. So now I want to talk about some of the properties and the ways of constructing these positive ascending surfaces. So from a constructive point of view, one of the useful facts about them is that you can construct them rather diagrammatically. So in particular, any surface in C2, which is defined using a sequence of braids related by the operations 1 to 3, that is adding strands, adding positive crossings, and braid isotopy and positive braid stabilization and destabilization. Any surface that you build using those operations will be a positive ascending surface. Okay. This will become clear later what the connection between braids and ascending surfaces is. This will be made clear later. But another useful fact as an exercise, every positive ascending surface in a thickened 3 sphere in C2 is isotopic to a symplectic surface with respect to the standard symplectic form on C2. The key point is that you may need to dilate to stretch radially the surface, but eventually you can always make it symplectic. Okay, and in fact, something even stronger is true. And this is a result due to Boileau and Revkov and Rudolph. And it says that if you have any properly embedded positive ascending surface in the four-ball, I can find a smooth piece of a complex curve such that the pairs B4 sigma and B4 sigma prime are diffeomorphic. So this is useful in the sense that, for example, using the construction outlined at the top of the slide, we can construct by hand positive ascending surfaces. And then the theorem at the bottom lets us say that there's at least some surface in the four-ball which is diffeomorphic to our initial surface and which is itself actually realized as a complex curve. So even though positive ascending surfaces are rather flexible, they stay very close to the realm of complex curves. Okay. So in order to flesh out the connection with the theorem 1, which is stated in terms of braids, we need to unpack exactly what the connection between transverse links and braids is. So the first observation in that direction is that any braid can naturally be viewed as a transverse link in R3, and thus in S3, using the rotationally symmetric contact structure that we were looking at before. So in particular, here we have the figure, and we have the z-axis in the middle, and a braid is a knot or a link which always has non-vanishing angular tangent direction. And so in particular, if it's sufficiently far out from the braid axis, the z-axis, it will be transverse to the contact planes, which twist up so that they get closer and closer to the half planes that emanate from the z-axis. So that tells us that we can naturally represent a braid as a transverse link. And conversely, combining work of several authors, we have that every single transverse link in S3 is transversely isotopic to a braid. And while that representative won't be unique, two braids, beta and beta prime, are transversely isotopic if and only if they're related by braid isotopy and positive braid stabilization and destabilization. And so you might see here where now the different ingredients of the first theorem are coming into play. In particular, the result at the bottom explains the third type of operation in theorem 1. Okay, so with this sort of language in hand, the relationship between braids and transverse links, we can refine and generalize theorem 1 to adapt it to positive ascending surfaces. And so here I'm just restating it and highlighting what the differences are. So if sigma is now a positive ascending surface in S3 times the interval, so that includes complex curves, but it's more general, and it's co-bounded by some transverse links, k and k prime, then k and k prime are transversely isotopic to braids beta and beta prime, such that beta prime and beta are related as in theorem 1. So we have these three operations for going from beta to beta prime. Okay. So this is a really useful structural result so we can understand topologically what this complex curve or what this positive ascending surface more generally looks like. An important point is that we can generalize ascending surfaces naturally to arbitrary Stein cobordisms between contact through manifolds, and the same results are true. The one caveat is that now, as I mentioned at the beginning, we also need to allow for some operations which change the topology of the level sets of the ambient four manifold. So now instead, we'll have to work with arbitrary open books instead of sort of the open book with disk pages that's familiar from the S3 setting, and we'll have a richer set of operations for describing the change in the level sets of both the braid, both the complex curve, and the ambient manifold. Okay. And so for the sort of final chapter of this story, I want to take these results and relate them to transverse invariance and link Floer homology. Okay, so given a link that's transverse to a contact structure in the contact 3 manifold, you can naturally assign to it an element in the link Floer homology that is invariant of the link up to transverse isotopy. And so here I'm thinking of the hat flavor or the minus flavor of the link Floer homology. And this was reframed by Baldwin, Velovic, and Verteschi using braids. And although for our context, when we think about braids with respect to the standard open book for the 3-sphere, which has disks as its pages, their formulation holds in any open book and allows them to work in arbitrary contact through manifolds. So in our setting, just to give a sort of a concrete picture of how this invariant is defined, let's take the braid to be just sigma 1 in the 3-stranded braid group. So topologically, this is just an unlink, but in particular, it's a 2-component unlink. But this is a particular braid representative, and it associates some particular transverse representative. And I'm going to schematically describe how the braid formulation of the transverse invariant works. So we take the disk with 3 marked points for the 3 strands, and we have to put down a basis of arcs, and that's what we see in the red curves AI. And the Heegard surface, or our Heegard diagram, is just going to be 2 copies of the disk, so it'll be the 2-sphere with 1 copy of each of the 3 points on each side. And the alpha curves are going to come from just doubling AI. The beta curves, on the other hand, on half of the surface will be perturbations of the AI, and on the other half of the surface, we take those AI curves and we apply the braid to them by viewing the braid as a diffeomorphism of the disk that fixes 3 points. And so that's what we have here depicted in blue, and together this naturally sets up a Heegard diagram for this knot in S3, or in this case, this link in S3, and there will be a unique generator supported on the left side of the diagram, and that's going to correspond to the transverse element, the transverse invariant in link Floer homology. Okay, so part of the utility of this framework for our purposes is that it gives us a really natural set of Heegard triple diagrams whenever you either add a new strand or introduce a new positive generator. And so using this, it's straightforward to construct a homomorphism. So if I have transverse links K and K prime that co-bound some positive ascending surface, then there's a homomorphism taking the transverse invariant of K prime, which is at the larger cross-section, to the transverse invariant of K, which is at the smaller cross-section. Okay. And so the techniques that go into proving this sort of build on work of Baldwin, Velovic, and Rateshi. And also later on, there's similar work by Lev, Tostopiev, and Hellip. But this proposition, for example, is sufficient to prove some useful non-vanishing results. So in particular, if you have k and k prime as above, then whenever k has non-vanishing transverse invariant, the same is true of k prime. And so, for example, any transverse knot that bounds a complex curve has non-vanishing transverse invariant. And this holds not only for knots in S3 bounding complex curves in the four-ball, but for knots in Stein-filial contact, three manifolds, bounding some complex curve in a Stein domain. Okay. But in fact, something stronger and more useful is true. So this was recently strengthened independently by Andras Juhas, Maggie Miller, and Ian Zemke. And what they showed is that, in fact, the transverse invariant is functorial under the natural cobordism maps on link Floer homology induced by a positive ascending surface. So that is, if sigma is a positive ascending surface in a thickened three-sphere, then for a suitable class of decorations on sigma, the link cobordism map associated to this decorated surface preserves the transverse invariant. And in particular, if K has non-vanishing transverse invariant, and for example, if K is empty, then that tells us the actual link cobordism map associated to the surface is non-zero. And this non-vanishing of this natural link cobordism map is useful not only for studying the knots, but now actually for studying the surface sigma itself and surfaces that are related to it. So in particular, Juhas, Miller, and Zemke use this to help detect families of smooth surfaces in the four-ball that are all isotopic through homeomorphisms of the four-ball, but they're not equivalent under any diffeomorphisms of the four-ball. Okay, and the result holds not only for positive ascending surfaces in the thickened three-sphere, but more generally for positive ascending surfaces in arbitrary Stein cobordisms. So a final note in this direction, more broadly, this also provides a framework for thinking about Legendrian invariants. In particular, there's many questions about the naturality of the Legendrian invariant under Lagrangian cobordism. And this, the results of Juhas, Miller, and Zemke, together with the structural results proven in Theorem 1, provide a framework for proving that functoriality in the Lagrangian setting by perturbing the Lagrangian to be a positive ascending surface. And so this can always be done for quote-unquote decomposable Lagrangians and should also work in the case of regular Lagrangians. Okay, so I'll end it there, and thank you for listening.